With our current understanding of atomic structure, using the Bohr model, we can now take a chance to look at today's periodic table. This is going to be our best tool throughout the chemistry course. So this short video is just to go through some vocabulary, terms you should be familiar with, and the first 4 periodic trends, all of which you should know. Let's look at these 4. The first one is how the periodic table is organized. When the periodic table was first organized, it was done by atomic mass by Dmitri Mendeleev. Kind of an interesting guy, and if you're using the Zumdahl textbook, it's got some nice little footnotes on Mendeleev. For example, that he took a hot air balloon ride back in the 1860s, 1870s, so that he could view an eclipse of the sun. Dmitri Mendeleev was a Russian scientist. He was quite surprised that there was an organized nomenclature for organic compounds, but nothing had been done for inorganic compounds and the elements on the periodic table. So when he did it, remember that scales were pretty crude. They didn't know anything in the 1870s about protons, neutrons, electrons. So he was working simply on mass, atomic weights. And so he organized the periodic table by atomic mass. Now, for the most part, that holds true that the elements on the periodic table, as you increase, going across the periodic table, their masses do increase. But a great exception to that would be looking at argon and potassium, because argon actually has a higher atomic mass, atomic weight, than potassium, and yet they're flipped on the periodic table. Years later, 1920, right around World War I, a British physicist, Henry Moseley, noticed in some of the work he was doing with bombarding atomic structures with different types of radiation, that from the patterns he saw a correlation with atomic number. So it was about 1920 that Henry Moseley changed, and this is the way today's periodic table is organized. Today it's organized 1, 2, 3, 4, 5 by atomic number. Interesting story about Moseley. He was young. He was very talented. And when World War I was going on, they shipped him off to fight on the front lines, firing a rifle. He was killed. And his loss was such a loss to the scientific community that was one of the first times when they said, oh, wait a minute. Maybe our great scientists, our great minds should not be out there firing guns. Maybe we can put them to use in a better way. One person that I want to call your attention to is Glenn Seaborg. Glenn Seaborg has done an awful lot to advance scientific education, chemical education. And when Seaborg did his work, he was really young. He thought he had found the first transuranium elements. If you look at elements on the periodic table, what you see is that most of the elements are naturally occurring. There are 90 naturally occurring elements up until number 92, which is uranium. After that, none of these existed. And Glenn Seaborg actually found elements 93 and 94. He named them after the planets Neptune and Plutonium and Pluto, calling them Neptunium and Plutonium. And because he was the discoverer of these elements, he also got to give them their abbreviations that we see on the periodic table. NP for Neptunium. And it was logical that he would have named plutonium PL, but Glenn likes to say he just liked the sound of PU. So he had a great sense of humor, and his laboratory out in California, as you can see, is responsible for a lot of these elements, because we have americium, berkelium, californium, Einsteinium, Fermi for the Fermi labs in Chicago, Lawrencium for the Lawrence Livermore Labs out in California. And so a lot of these came out of the California work. I want to read just a passage or two here that I think you'll find interesting. And these talk about why would the United States want to keep secure some of the information about these elements that were being discovered? Well, the answer was simple. Traces of the elements were discovered in the residue of the first thermonuclear hydrogen bomb explosion in November of 1952, an explosion that obliterated a small island in the Pacific. In such an explosion, some uranium-238 is converted by extremely intense neutron bombardment into uranium-253 and gamma radiation. The uranium-253 is then spontaneously transformed by beta decay into things like Einsteinium. And another quick passage about naming the elements, it says that the new elements were named according to their positions on the periodic table. So, for example, europium, element number 63 here, was named for the continent of its discovery. So americium was an appropriate name for element 95. Gadolinium, number 64, was named for a famous scientist. So it made sense to name this after the Curies. And the problem with naming element number 98, californium, was that it's the origin of the name of its rare earth dialog, dysprosium, didn't have a matchup. And so dysprosium literally means hard to get at. So the Berkeley group decided to ignore precedents and name it for the state of California, which seems to be kind of appropriate because America's 19th century settlers found California hard to get at. Okay, so if you look, all the elements past number 92 are not in black. This means that they're not naturally occurring. All of these had to be made, and we'll talk about how these were made in class. Seaborg then was responsible for the first transuranium elements, and when he found these elements, he had to position them on the periodic table. The periodic table at that point didn't look like today's periodic table. There was no block here. It was part of the main body. And he had to make the decision to move this down into a separate block on the periodic table. Let's go back then to some of the other periodic trends, which include that as you move across a periodic table, you always see the same patterns. You see that moving from left to right, we have our metals. We go across till we come to the staircase where we have our metalloids. We have our nonmetals, and every row across the periodic table ends with a noble gas. So we have this pattern of metals to metalloids to nonmetals to noble gases moving across the periodic table. We've also talked about sublevel blocks. The sublevel blocks include, as you can see here, the S sublevel block, the D sublevel block, the P sublevel block, and down below, the F sublevel block. So, I'm going to show you the sublevel blocks one more time. The P's, the F's, the D's, and the S's. All right? Now, something we haven't talked specifically about is families. If we're looking at families, families or groups are vertical columns on the periodic table. There are 8 major families, often referred to as the representative elements. If we look, we want to know where these 4 major families are located on the periodic table. So turning here, we see that the first family is referred to as the alkali metals. The second family is referred to as the alkaline earth metals. Very clever, because the word alkali refers to a substance that is basic, a base, we know where our good bases are on the periodic table. Moving across, sometimes you hear the term chalcogens for this family, but it's not very common. So we move on to the seventh family. The seventh family is the halogen family, and then here the noble gases. What do families have in common? They have the same number of valence electrons. And because of this, they have very similar physical and chemical properties. All of these elements in the halogen family, 7 valence electrons. To get to an octet, a filled S&P, they need 1 additional electron. Then we have our series. The series is going to be the highest energy level. And as you can see by the red arrow, this is going to be a horizontal row. If you go back to your periodic table, what you'll see is that along the side we wrote the numbers 1, 2, 3, 4, 5, and 6. And that tells us the highest energy level, S's and P's. So if you're asked to look at the second series, either a series or a period is a horizontal row. This is the second series, lithium through neon. The third series is sodium through argon. And the fourth series would be potassium through krypton on the periodic table. Other than that, there's just a few terminology, words that you need to know that you can find in Chapter 8 with the periodic table. Transition metals. The D sublevel block is referred to as the transition metals. Then we have the inner transition metals, and that makes sense because if we look here, inside the Ds we have these 2 stars on our periodic table telling us that we want to insert the F sublevel block. So the F is our inner transition metals. Specifically, we refer to these, the 4F sublevel block, as the lanthanides or the lanthanoids, either one. These are elements 57 through 71. And then we have the actinides, starting here, the actinides, which are elements 89 through 103. You know, it's kind of interesting. I don't think you'll ever be tested on this or see this on a test, but lanthanum starts with 1 electron in the 5D sublevel block. When you get to hafnium, it has 2 electrons in the D sublevel block. But by the time you get to hafnium, all of the 4F sublevel block electrons have been filled. Kind of interesting there. So what you are encouraged to do at this point is to familiarize yourself with names and terminology so that we can go on and do the great chemistry of looking at new periodic trends.